Beginning, the disturbance increases by 6, which would make the system move away from the nominal steady state if I did nothing with the manipulating. If the input stayed at 0, then I would reach a certain new steady state. Okay, actually, let us ask a question. First question. If U is not changed, and this becomes question 2. What would the new steady state value of y be? Of y prime. So that's the question. So, we found this. Let me write down the result of this equation. Let's see how we're doing the time. 17 minutes. So, the result of this equation, guys, is that if I have y prime bar equals from y prime bar equals GU of S, U prime bar plus sum of GDI of S, DI prime bar. If a new steady state is reached,
what's he doing?
which requires stability, and that the inputs reach a new steady state, it is going to be sorry, my handwriting when I'm hurrying gets worse. It will be y prime at time infinity is GU of 0, U prime at time infinity plus sum of GDI of 0, DI prime infinity. So any input that changes will have that. You understand? That's the consequence of this. That's the y prime infinity. What do we have here? GU of 0, U prime infinity. Plus sum, this is what? This is GDI of 0, and this is DI prime infinity. So this is a general equation. You can put this in a box. It's an important equation. Very useful for example of this. Okay? So, yeah.
Are we going to have to do some tests?
Absolutely. Yes, most definitely. All right. So, how do I answer this question? If U is not changed, what is U prime? 0. Guys, in this case, U prime infinity is 0. It didn't change. What would be D1 prime infinity? 6, right? You can say it by 6. So, the answer is, what would be the new steady state if I didn't change that? Y prime infinity would have been, and I don't care what GU of 0 is, times 0, plus GD1 at S equals 0, times D1 prime infinity. So the new steady state would be minus 5 over 0 plus 2 times e to the 0 times 6. So minus 30 over 2 minus 15. So the system would go to a new steady state 15 lower than the original steady state. Now let's address my original question. I'm asked how much should we change U to ensure that the system ultimately returns to the original state? Okay, I'm going fast. Do we digest this, guys? First important question to understand. You understand that the final value theorem tells us that if I have stability, and if the inputs reach steady values, the new steady state for the output is going to be given by this equation. This needs to get understood first. Adam, your question?
No.
How we do? Daniel, okay?
Let's say e to the 0 times.
Yeah, 6. Yeah. 6 is increased by 6. That's the GD1 of 0. Okay, that's GD1 of 0. Means whatever you have S, you put 0. Okay, so it's the GD1. Christian, you have a question? No. So do we understand this equation? That tells me if I have the transfer functions, just take 0 for where I have S and put the constant values that my inputs get. And I'll get immediately, without having to do inverses and partial fractions expansion, what will be the new steady states. One okay?
Yeah.
Brian?
Yeah.
Alright. So, you understand the answer that if I did nothing, if U is not changed, if it stayed at its nominal value, my input would decrease by my output would decrease by 15, minus 15. Now, I'm asking here, if I time it, how much should we change U to make sure that the output returns to the desired value? So the second question, and let me write it here. So now we are going to be changing the input. Let's say we change it to the new value y prime infinity. Okay? So we will change it to the new value u prime infinity. I will have y prime infinity is gu of 0 times u prime infinity plus gd1 of 0 times 6. Right? Unfortunately, I hit the problem. What am I telling you? What do I want y prime infinity to be? I don't want it to become minus 15. What do I want it to be? 0. So I must have 0 equals gu of 0 by how much I'm going to be changing my manipulated input plus gd1 of 0 times 6. In other words, what is gu of 0? I'm looking at my gu and I'm putting wherever I have s 0. So that's going to be 3 over 0 plus 4 e to the 0 times the unknown u prime infinity plus the gd1 of 0, which we already did that, minus 5 over 0 plus 2 e to the 0 times 6. So that means I must have 0 equals 3/4 y prime infinity minus 15, right? And we'll solve for u prime infinity. Should be 4/3 to 15. In other words, last one. Okay? And now you see all the example problems, you'll be able to see how they're done. That's part of the reason I decided not just to have time to look at all the exams and be able to do them. Okay? So you understand, if I have the transfer function, evaluating it at 0, if I'm stable, it tells me what the new steady state is going to be. Okay, now, next issue is, how do I approach the new steady state? One question is, will I approach with oscillations or without oscillations? So let's say I found out, in this example, I went to minus 15. So I was here at 0, y prime, and I end up at minus 15. How do I go from here to here? Will I go maybe like that? Or will I go maybe like that? This is on oscillations. This is without oscillations. I can tell that entirely from the poles of the transfer function, which are the two cases. So, number one, we discussed stability. Number two, we discussed new steady state. Number three, oscillations. So let me summarize what we're doing. Number one, we discussed stability requires all poles with negative zero. Number two, we discussed is stable and inputs that reach constant values. New steady state is going to be y prime infinity equals 0, 0, u prime infinity plus sum of gdi of 0, di prime infinity, consequence for the finite thing. So hopefully those two are understood. Is that okay? Okay, number three, oscillation. Okay, and over here, two things we're discussing. First of all, what I would call mathematical oscillations. If even, or by the way, poles are either real or complex conjugate pairs, because the coefficients of the A matrices are all reals. So the determinant Si minus A we have is a polynomial of real coefficients. And polynomials of real coefficients have either real roots or complex conjugate pairs. We will never have a complex root without having the complex conjugate pair. So if there is even one complex conjugate pair, there will be mathematical oscillations. Mathematical oscillations may be, if you have an oscillation at the 7th significant figure, are you ever going to see it? No. Our measurements are good at best 3 significant figures. So we would never observe an oscillation that happens at the 7th significant figure. So if I have a complex conjugate pair, I will have, mathematically speaking, oscillations. I may need to go to 100 digits to be able to see it, but it exists. However, from a practical point of view, more often than not, even then, it will not exist. For them to be observable, be able to see them actually, conditions. Must be satisfied. Must have two conditions satisfied. And the okay, 3 minutes. All right, instead of talking about those two conditions, let me go back. We'll need that anyway, and discuss a little about stability, understanding. We know, we have 2 minutes, that's a 2-minute discussion. We know that y prime bar is, let's say, gz of s, z prime bar, and let's assume for the moment that I have just distinct poles. Every pole is multiplicity 1. So that gz of s is going to be something over s minus pole 1 times s minus pole 2, s minus pole 3, and so on. And if, let's say, the step change is a constant, let's say z prime is equal to delta z. What's the Laplace transform for constant? Constant over s, right? Maybe it was probably spent. So z prime bar would be delta z over s. Right? With me? What would be y prime of t? Well, you do the partial fraction expansion, get the coefficients, but what do you get? You get something over s from here. You have something over s, so it will be, let's say, C11 over s plus C21 over s minus P1 plus C31 over s minus P2, and so on. So, sorry, y prime bar. So y prime of t would be the intercept. So it will be C11 plus C21 e to the P1t plus C31 e to the P2t, and so on. So that's going to be what y of t is. What happens as t goes to infinity? If even a single p is positive, it goes up. If all the p's are negative, what happens to all those terms as time goes to infinity? Disappear. And you only have the constant, which is the new steady state. So that's how stability comes about. Okay? And if you have higher multiplicity, you simply have t e to something, like we saw in the example we just did on Excel. Come on, I'm 30 minutes early, Katie.
Can you repeat?
30 seconds.
Can you repeat what you said?
Yes.
About the ease?
Yeah. So you understand that these are my poles, right?
Yeah.
So the partial fraction expansion will be something, I have this from the z prime bar, and this is from the gz of x.
Yeah.
So y prime bar partial fraction expansion will be constant over s, plus constant over s minus p1, plus constant over s minus p2, and so on. The inverse of that from the dictionary, something over s gives me a constant. Something over s plus p1 gives me e to the p1t. Okay? Remember, 1 over s plus a gives e to the minus a. So a is minus p1, e to the p2t. So, what is phi prime infinity? It's the limit as t goes to infinity. So if I have a positive number here, I don't get how small it is. E to the pt is positive, still blows up, no matter how small the positive number. I need to have all the p's negative for it not to blow up as t goes to infinity. No? If even one p is positive, e to the pt blows up as time goes to infinity.
Saturday and Sunday.
Okay, means we don't get it. What is e to the 0.01 times t as time goes to infinity?